Hi, welcome back. And in this video, we're going to be talking about anytime search, and we're going to be using anytime weighted A* as the first anytime algorithm that we'll be having a look at. This is really important. I think anytime search is one of the go-to methods for difficult problems, but I think this is something that outside of the academic world, people are very there's not much information out there. People may not be aware that this entire field of study even exists, that these algorithms are probably the go-to. They're probably going to be better than the traditional A* that you might just be plugging into your games from the get-go. What is anytime weighted A*? Well, in the last lecture, we spent a lot of time having a look at weighted A*, right? We're showing that on average, weighted A* is substantially faster than A*. We're able to get solutions much quicker, right? And so this is important in environments where the amount of time you can spend searching is limited. And then what we're getting from weighted A* is that we have these bounded suboptimal solutions, right? So our solutions are at most W times worse, and we are able to control how much we're okay with trading some of that solution quality for a speed up. But if we were to consider this a little bit further, well, oftentimes, right, you have been given some form of time budget. You're told, I have 2 seconds to plan, maybe I have 500 milliseconds, whatever it is, right? That is where we were kind of using this weighted A* to just try to get a solution quickly. The weird part about that, right, is maybe that takes 50 milliseconds, however long it takes. Well, the whole rest of the time budget you have available is unused, right? We actually just we found the first solution. Sure, it was suboptimal, it's whatever, we already made that trade-off, we were okay with that, and then we stopped. That is silly. So anytime search is a framework that is tuned for these kind of problems. We are using the idea that, of course, if we have time remaining to continue searching, we shouldn't just stop. We actually should make use of that time. And so what we're going to be doing, what anytime search really is about, is iteratively improving a solution, okay? So we're going to be finding a solution very quickly using something like weighted A*, right? Find a solution really quickly, it'll be suboptimal, but within some set budget that I still have remaining, I will attempt to iteratively improve the solution. I will not halt search, I will continue search so that we can actually find better solutions. That is why anytime search is extremely fundamentally important, right? From the get-go, if you have a time budget, you're not guaranteed that your A* will ever return the path in time, right? So your player might just not have a path to move. So you need some form of plan to start moving. Great, okay, that's our fast suboptimal solution. And then anytime algorithms are going to improve the solution within the time allocated to them as their resource. This relates then to the idea of the use cases that anytime algorithms are really important for. Number one is the idea of uncertain time budgets as well, right? Some problems, you aren't given a specific amount of time, you don't know exactly how long you're allowed to continue the search. So in these situations, well, anytime algorithms will be much better, right? Because, hey, we get a solution really quickly. So we feel more safe that we have a solution to return to the user, right? We don't fail search altogether. And then within however long that is, we just keep trying to improve, yeah? This is also why then anytime algorithms are extremely useful for dynamic environments. So by dynamic environments, I mean environments where, say, doors might open, doors might close, maybe regions of the map, the weights change, right? So maybe it becomes a bit more costly to move through this area, maybe it's flooded, maybe there's a forest has grown, a wealth of options are available. But in these situations, right, when things change between your planning and then when you go to execute the path, that's where oftentimes the algorithms have to be really quick, right? You want a feasible path fast, right? Before things in the environment change, and then you might have to call a bunch of replans very quickly, right? Oh no, I've encountered a door that I was not aware of at the time of previously planning. I need to replan. Anytime algorithms can be extremely useful in these domains. Finally, there's also the idea of real-time planning. So this is its entire subfield of its own. So I'm not going to talk about that too much here, but in real-time planning, or I think there's many different names for it, these are just the kinds of problems where essentially you have to be interleaving planning and execution. So usually the way we've been talking about all these problems, sure, maybe I'm talking about like fast time budgets, but realistically it's kind of been that academic pure sense of we plan a path, we go do it, okay? In the real world, it's not as simple. So especially if you have like a robot in a real world scenario, what you're going to be doing is having to interleave the idea of planning in real time and then checking your execution. Okay, so you need to come up with a plan fast, right? An initial plan, it might not be the optimal plan. Get your robot moving and then adjust as the situation unfolds. For example, with execution, it's not always 100% guaranteed. You tell your robot to move straight, maybe there's only an 80% chance that happens, or maybe you get stuck, or maybe things change, maybe it's a dynamic environment. There's a whole lot of things that mean with the interleaving of the two ideas together, well, the advantages of anytime algorithm become apparent. Okay, so with all of that said, let's dive then into actually the idea behind anytime search. So the idea then, which I've said before, is that we are going to be essentially finding a solution fast, right? So find a first solution fast. Now, this does not have to be, you're not expecting it to be a high quality solution. It just needs to be a valid solution, a valid path. And then we will iteratively improve it within a fixed time budget. Okay, so I've talked about that already, so I think that hopefully is pretty apparent for what we're actually going to be doing. Now, I just want to keep in mind a couple things before we get started. I'll then erase these two things and we'll talk about actually exploring this through the lens of Anytime Weighted Astar, okay? I'll show you how we're actually going to be using some bounds, some clever tricks to know when we actually stop. Okay, so to keep in mind though, from the get-go, while we're doing the explanation of how these algorithms work, remember, anytime algorithms are not just a magical bullet, so they can still absolutely run out of time. We'll show that if you give it enough time, it actually will prove optimality. So given enough time, it keeps iteratively improving the solution until at some point it goes, oh cool, this must be the optimal solution. Well, that is only the case when we have sufficient time to do so. Most of the times, right, the use cases we're discussing, you probably don't have time. The other thing to keep in mind is that Anytime Weighted Astar is not going to suddenly mean that you never fail from the get-go. When you have very little time, or even when you have a reasonable amount of time, anytime algorithms can still fail. Anytime Weighted Astar can still fail. This will happen in situations where the first solution is not found within the time budget that you've actually been allocated, right? What we've just seen in the previous video that Weighted Astar is on average much faster. However, in certain situations, it is substantially worse as well, or maybe it's just hard for all algorithms together. There's no guarantees. You don't have a guarantee if it's within a set amount of time that you will even obtain the first solution and then be able to iteratively improve, okay? So that's something really to keep in mind. You're going to need, right, that's leading us towards the idea that we really need our first solutions to be quick, right? That's kind of like the backbone of this whole idea. We need to have a valid backup plan to start moving, to start your robot or your player moving in the correct direction in the case that we run out of time and so that we don't fail. Okay, so let's dive into it then and discuss Anytime Weighted Astar. Okay then, let's have a go at describing Anytime Weighted Astar. Right, so the idea that we've seen before is again that we want to find a first solution fast, right? This is where we use Weighted Astar, okay? To find a first solution fast. Okay, where do we go from now? So we've done search, we weight the heuristic, right? So we hopefully beeline towards the goal, we find a solution really quickly. It's not a high quality solution. And so what do we do next? Well, this is where we deviate from weighted A-star. Instead of simply stopping, right, we will actually continue search in order to iteratively improve the solution. Okay? Now, what do we do at the end? Well, we need to discuss when we actually get to stop to terminate the algorithm. We're going to terminate the algorithm in two ways. Number one, we just run out of time, right? That was absolutely a situation. We had a time budget. Maybe we just, we do as much as we can in the time budget. It runs out. The other version of this is, I mentioned this briefly, but we can actually prove optimality, right? So given enough time, Anytime Weighted Astar is guaranteed to tell you, hey, I have now proven that this is the best solution it can possibly be. Let's write that down here, but as the little spoiler ahead of time, in order to prove that, we're actually going to have to, in Anytime Weighted Astar, exhaust the entire open list, right? So we can only prove optimality when there is nothing else that can possibly improve the solution further. So terminate when out of time or when open is exhausted. Okay, so when we run out of things to look at next. So before I talk about what we're doing during search, well, this is really begging some questions now, isn't it? And that's related to the right-hand side here. Okay, we're talking about proving optimality. How can we even reason over this? Well, anytime algorithms, and specifically Anytime Weighted Astar as well as an example of this, well, all of these anytime searches are going to be using the concepts of an upper bound and a lower bound. So what is an upper bound? Think about this, right? We're doing search. We've found a first solution really, really quickly, okay? We have a cost associated with that actual path. We were conducting search by what we'd be calling FW, right? The weighted F value. We know that this path is not optimal, but it's the best one we've found so far. If we had a bunch of nodes in our open list, well, we can start to look at those and go, okay, your promise, the best this node is promising us at all, is already worse than the path we've already found now, right? So that is where some of this power is coming in. What we're doing is we're tracking an upper bound, which is essentially just tracking the best solution thus far. Okay, this is the best cost we've seen. We get to prune, we get to throw away all nodes that can no longer, even in their most optimistic case, promise to improve upon this, right? It was going to be worse anyway. That's not a useful avenue for search. That's our first exciting part. Now we get to the idea of the lower bound. Well, the lower bound is, as I've been kind of saying in that explanation, the lower bound is our optimistic estimate, okay? So not only do we have, hey, this is the best one we've found thus far, but we have like this, using our heuristics, right, our regular A-star, the F values are promising the closest, the best path that we think is possible, right? During search, during a regular A-star, of course we start to see that the F values get pushed up over time, right? Often, we now discover more obstacles in the map, we realize that we have to do a bit more of a detour, right? And so your optimistic estimate, right, your F values remaining in search, well, they're going to increase slowly. Nonetheless, it is an optimistic estimate. Our heuristics are going to be admissible, right? They are underestimating the true cost, or are going to give you the exact cost in an ideal sense. So this is the lower bound is our optimistic estimate. So optimistic estimate. This is the best we think we could possibly do, our age-old F value, right? Now, this best solution thus far, that was the cost of the optimal path. What's, I guess, important to say in that is that initially, right, before we find our first solution, the upper bound starts at infinity, right, because we haven't yet found a path. We don't think there is any version of the path. It could be an unsolvable problem. Okay, so we're starting to see, right, so we have now this idea of a upper bound. This is the cost of the best solution we've found thus far. Right, anything above it, we don't care about. It's not promising, we can throw it away, right? We can prune these nodes entirely from the search space. That's exciting. But then we also have this idea of a lower bound, and as I've been discussing, right, this is our optimistic estimate. Well, over time, that is going to be gradually raising throughout search, right? As we exhaust more of the open list, well, we're essentially proving that yes, there were going to be a bit more detours, a bit more of a roundabout way that was necessary. And in that case, your F values, the lowest F values in your open list, are going to be slowly raising. The other aspect of this is the best solution thus far. Well, as we encounter and improve the solution more, which we will still have to discuss how we're doing that here, what that means is we can find better solutions, right? It was bounded suboptimal before. Maybe we find some shortcuts this time, or we're a bit more exact in the version of the path we're having a look at. We are, over time, going to find different solutions that have better costs. So what that means is your upper bound, not as much in a smooth fashion, but it will start stepping down, right, with each incremental cost improvement. Those could be small as well, of course. And so what we're seeing is that we're actually reducing the bounds of our algorithms, okay? What does termination mean? Termination means that our upper bound and our lower bound cross, they reach each other. At the time that we see this crossing of upper bound and lower bound, that means we know we're done, right? We can essentially terminate search. Hey, the solution, the best one I found thus far, that's when we know we're done, right? Hey, the best solution I've found thus far is also my most optimistic solution. Well, ta-da, that means I've finally done the work. I have proved to myself that this is the optimal cost solution. I can simply return the path. That's awesome. Now, there are some caveats. This is where I think before I start talking about why we have to, right, when open is exhausted is what I've listed as the termination condition here. Based on this upper bound, lower bound business, I haven't really discussed why this is necessary, right? So if they cross, surely we could just stop when if everything left in the open list is all the same F value that's still telling you it's the same as the cost of the best solution, we should be done, right? That is not the case. Let's discuss that in a second. Finally, just before we get over here then and discuss the intricate details, well, the expansion priority ordering, we are going to be expanding nodes by the weighted F function, right? So we're expanding things in order of weighted A star. So even after we find the first weighted solution, we're still going to be ranking all the nodes by that FW. So G of n plus W, right, times H of n. Okay. Now, let's discuss what's happening during search. Okay, so let's then talk about what's happening during search and write down some of the things I've just said verbally. Well, anytime weighted A star, right, is essentially we are going to be updating the upper bound each time the solution is found anew. The goal is expanded, right, with a better cost, of course. Okay, so that's the first part. We're iteratively improving the best solution we've found thus far. Well, as we do that, as well, the main idea there is that, well, we get to prune, right, by the upper bound. So we are going to prune all nodes in open with F, their actual F costs, not FW, right? With F of n, which is strictly greater than the upper bound, right? These are the nodes that are not promising. We get to prune them. Now, the final aspect of this, the bit that relates to when open is exhausted, right, and how that relates to the crossing, well, this is where we kind of have to walk through an example to understand. I'm going to do that. Future me is going to do that in a second with a bit more of an animated helper. But what's going to be happening is that during search, anytime weighted A-star, unlike both A-star and weighted A-star, we have to do something differently. Okay, so regular A-star has the guarantee that every expansion is optimal, right? Every single time you expand any node in the entire search, you have proven that that is the best path possible to reach that node. So when we expand using an admissible heuristic, consistent heuristic, under regular A-stars f equals g plus h, we have this guarantee. Of course, weighted A-star does not have this guarantee, yeah? We're expanding nodes explicitly in a suboptimal manner, hoping that it gets us there quicker. The difference is in weighted A-star, we just happily accepted that trade-off, right? Like we find the solution, we stop, we return it. We never had to think about all the nodes that we moved over to closed, right? All those suboptimal expansions, they weren't related, they weren't necessary to reason over. In Anytime Weighted A-star, we're of course trying to improve the global solution. What this means is that when we encounter new paths, there's perhaps new shortcuts, there's better versions of the path, symmetric equivalent topologies, all these things, right? As we're iteratively continuing search, we will rediscover better ways to reach certain nodes than we already expanded them with. What that means is that we are going to actually have to we're finally going to have to, we've never had to do this, reach into our closed list, into our little graveyard over here, and then pluck out the respective nodes and put them back into open with their now better path cost, okay? So that additional bookkeeping and that additional work is absolutely necessary for Anytime Weighted A-star to actually be finding the better versions of the paths, right? And continue to look in the correct way to eventually prove our optimality. Hey, so I think it's a good time to go through a small example of how the algorithm actually works. So what we're seeing here is that, right, we're going to expand nodes by their weighted F value first. So what we're going to see is that the algorithm is going to beeline towards the goal. So we see that here as we begin to start expanding. So we go up across the diagonal first because it thinks it's the closest, and it's going to proceed expanding nodes directly towards the goal. You note even when it gets blocked by this obstacle here in front of the target, well, it's going to go down. It's still just, it's 10 times more likely to keep trying to move towards the goal. So it continues, it brute forces its way through, and we get to the first interesting point here. So at this point in time, we have found the target T. We found the target T with a path cost of 7.83. So on the right here in the statistics, you can see that the upper bound has now, instead of being uninitialized at infinity, it has now been updated to the cost of the best solution we've found thus far, which is 7.83, okay? The lower bound is going to be constantly changing throughout search, but that is essentially the most promising F value, regular F value, so F equals G plus H, in the open list at the time. So what happens next? Well, essentially, what we see now is that there are all of these X's. So we have now found a solution, we have an upper bound, and we now look in our open list and we start to prune things that are explicitly unpromising. So every single one of these nodes, its F value, its actual F equals G plus H, unweighted, that is its optimistic estimate of how soon it could possibly reach the target, right? And so what's happening is that every single one of these are unpromising directions. So they are already in their most optimistic sense not going to improve the solution, and they'll never be useful in search, so we can prune them. So that's exciting. Now, the difference here is that weighted A-star, right, would have found the solution and it would stop completely. We're happy with returning this suboptimal solution. This case, we're going to continue. So the nodes in green still are nodes in our open list. The red ones are ones that have already been expanded. So we continue, right? So we expand D6, we expand B5, we expand D5, we expand D4. So this is the interesting point now. Now that we have gone back and continued to do these expansions, well, we finally see that we have now actually discovered a node, so D5 here. the path has actually improved. The G cost of reaching this node has improved now. So unlike regular weighted A-star, where we just expand things in a greedy sense and they get chucked into closed and they never come back. Then you also have regular A-star, which expands things optimally. So of course nothing ever comes back because you're guaranteed with regular A-star that every node expansion is the optimal path to that node. Here, we do need to bring D5 back. We bring it back from closed and put it back in open, and it might be something that we want to look at in the future. So we'll continue search, and you see that, yes, we do keep finding these re-expansions, and we keep progressing the search, and ta-da! All of a sudden, we re-expand the goal again, but this time with a cost of 7, right? So our upper bound now is moved from 7.8, and it's updated to 7. We have found a better solution, and we're not done just yet. So what happens is we will need to continue to essentially continue search and exhaust the open list, which we'll talk about immediately after this example in more depth. So you see that essentially now we go through, we do all these expansions. What you can note, right, is see how there's the grid cells with numbers around the edge that are non-colored. These are nodes that would have been otherwise generated, but because they're able to be pruned, right, because of our upper bound, we don't even have to add them to the open list. We don't have to deal with any of the heap operations involved. So that's also exciting. And so we continue all the way through. Finally, we've exhausted the open list and nothing came back. We've essentially proven now that there were no possible shortcuts we still hadn't found and expanded just because of the greedy approach. There's nothing left. Search has now concluded. We have essentially, our upper and our lower bound have reached each other, and we can now state that the solution we've found, this path cost of 7, that is provably optimal. It is the optimal solution. So that is Anytime Weighted Astar, and now let's jump back to discuss essentially why we need to do this final trick, right, where we exhaust the open. What's happening there? So let's write that down here. So then the last part, right, is from taking this idea of that we're taking nodes back from closed and putting them in open. How does this relate to the idea that the open list needs to be exhausted? Well, we need to remember our expansion priority. Our open list is ranked and sorted in order of the W greedy estimate, right, by FW of n. What that means is we can never know that based on this greedy ordering, that if there's still nodes in open, right, we don't know that if you expand the greedy version, we will take another node back from closed, bring it in, and its actual F value, right, might be a better cost solution. So we're unable to prove that the bounds are fully closed, right, and that there isn't some small improvement still available up until the point that we exhaust the open list, right? We showed that there were no more actual F values, this optimistic bound that could come back and then actually still improve our bound further. So that very last step there, well, we need to, unfortunately, in practice, we're exhausting the open list. So that's a little bit tricky, right? So then let's kind of take another step back and start to explore where Anytime Weighted Astar might succeed and where it might struggle, right? So what are the strengths and weaknesses based on this whole procedure we've discussed? Well, what are the main weaknesses? So Anytime Weighted Astar, as we've just seen, well, it's the idea that like termination is really tricky, right? Optimality proofs take a lot of effort, right? So Anytime Weighted Astar, actually we'll discuss in a second as well, oftentimes it actually gets the optimal solution really, really fast, which is awesome, particularly when we have this time bound. So especially if it's an uncertain time budget, at any point we could just get cut off and we might have already found the optimal solution quite a while ago. But it's the proving that the solution we actually found is optimal that takes the majority of the search time, oftentimes. That is a difficulty, right? That's a disadvantage of Anytime Weighted Astar. Similar, it's just in terms of, that is a disadvantage of using these approaches. Yeah, termination's tricky. Proving that our bounds have crossed is tricky. You're going to have to exhaust the entire open list, right? That can take a very, very long time. The other idea of this is that there are obviously these re-expansions, right? So the re-expansions can be really, really bad. In the worst case, we can have 2 to the n re-expansions, which is very, very, very large. And you know, so the worst cases of Anytime Weighted Astar can really stagger the usefulness of the approach. So this is a strong disadvantage of Anytime Weighted Astar. But what's good is actually we can mitigate a lot of these issues through the use of advanced and good heuristics, okay? So things like differential heuristics and CPDs, compressed path databases. I have videos on both of those on this channel as well. These are some of like, these are the leading, the most useful, most informative heuristics we can kind of come up with. They are often paired with Anytime Weighted Astar. It's worth doing and spending the time of this pre-computation because it really reduces the amount of re-expansions and the amount of work we have to spend really like proving this optimality and not being able to prune more nodes from the search space. So yeah, good heuristics can help mitigate these. Now, what are some of these strengths? Well, Anytime Weighted Astar is, first off, really good in any situation where Weighted Astar was already good, okay? So if you have experience with Weighted Astar, you can start taking those intuitions over the kinds of geometries and problems it excels in, and Anytime Weighted Astar, of course, will then similarly excel. There's this idea as well, right? There's obviously, we're weighting the heuristic by some W. We haven't really discussed how you pick W, and so I think that's very tricky and, you know, often problem specific. There's 2 sides to the coin, right? You're like, okay, well, obviously I really, really need a first solution fast. In the case that you have a really small time budget, I think, yeah, selecting a really high W is maybe good for you. However, more often than not, I think keeping your W reasonable, actually pretty low, is usually the better and the more performative version of this. So the original authors, I also highly recommend reading the Anytime Weighted Astar paper. It is one of the most approachable papers, I think, in this field that I've read. It's really a fantastic paper, and I think you can understand it. If you can understand this, you'll understand the paper, which is great. The authors actually talk about things like this. So in their testing, they see that Anytime Weighted Astar, surprisingly perhaps, performs very, very well even with, or it's even performing best with low Ws. So yeah, you don't actually have to raise W too high, right? I guess it's like this trade-off of the additional weighting didn't really like give you the advantage of choosing the faster path per se. And then when your suboptimality is a bit more limited, then the termination conditions and improving things can be a bit easier. So that's something to keep in mind. But yeah, so it's going to be in areas where Weighted Astar is good, AWA-star will also be good. Now, as part of that discussion, there's actually, I think also in the initial paper, they mentioned that there's the potential perhaps for actually weaving in like 2 different types of heuristics, right? So maybe you can use one heuristic to try to order your nodes for which ones to actually rank, but then within the nodes that all have the same F value, well, perhaps a second heuristic might be able to help you choose which ones to actually expand first. That's something to note as well. But otherwise, the main takeaway, the main advantage, the craziest and perhaps most surprising aspect of Anytime Weighted Astar, it can be faster than A-star. AWA-star can be faster than traditional A-star. This is definitely not like the norm, but it absolutely does happen, which in itself seems a very surprising result, right? So in the other videos, right, we've discussed, well, A-star is, right, like famously optimally efficient, right? So no algorithm that's not more informed can expand fewer nodes, right, up until tie breaking. That's like this original claim. But the key thing there is, right, like optimally efficient is, I think, very misleading because it's saying optimally efficient in terms of node expansions, which is absolutely not, it's one of the metrics, but it's definitely not probably the metric that we all care about more often than not, which is time or perhaps memory, right? Like these actual practical metrics of performance, right? You want your algorithms to run really, really quickly, and you want them to run without running out of memory, right, and failing in that way. Often memory these days is modern computing means usually we're pretty happy with that, but if you're in video games, again, maybe if you're given no resources to work with. Or technically some of the really, really large problems explode so much that memory is important. Nonetheless, the main aspect I think there is that AWA-star can be faster than A-star, right? It will expand more nodes. We have talked about in the past, right? We usually correlate, like linearly, this idea of node expansions to runtime. And more often than not, it follows, it tracks, right? But it's not always the case. How is Anytime Weighted Astar getting this improvement? Well, because of our idea of having an upper and a lower bound, what this means is it actually enables us to prune a series of nodes from the search space, right? We had all these nodes in the open list that have F values that are no longer promising, right? We've already found a new version of the solution that is better than what these nodes promise, off in our periphery, off in our frontier. So what that means is by pruning these nodes, right, we are essentially removing all of the actual practical and computing work that's necessary to store and maintain these in the actual open list itself, right? So the number of heap operations, right, every time you're adding more things into open or popping things or relaxing nodes, well, all of a sudden the efficiency of the algorithm and the amount of time it takes search to complete is actually faster, because by pruning nodes, even though we have the issue of re-expansions, well, we've actually gained an advantage in time by making this trade-off. So I think that's really exciting in its own right. And it places Anytime Weighted Astar pretty well. I think overall though, what I really want to say is that this has been Anytime Weighted Astar. I think Anytime Search is a really, really exciting avenue that I think is really underrepresented, perhaps outside of academia. Particularly I think for things like game dev. I think if you're implementing A-star already, I think you should absolutely have a go at implementing an anytime equivalent. Oftentimes, time is important, or having these failure cases for your agents, right? That's a critical failure. You need to return a path to the player when they asked for one. You never want your NPCs, your players, your agents, your robots to stand still, right? That breaks immersion. It is a strong failure case. Anytime Weighted Astar, sure, the concepts here we've talked a lot about, this is a very easy augmentation to A-star to implement, right? All you're doing is essentially just adding in a second F function where we're tracking the best cost so far and we're pruning, and then we just have this re-expansion idea. It's very easy to implement, and it has, right, these massive strong advantages in that when we have these unknown time budgets, we're able to return a solution. We get a solution quickly, so we essentially are more safe in guaranteeing a minimum threshold of performance for the player. And then we still usually are able to then actually just get the A-star's optimal path anyway within like these reasonable time budgets. The other thing as well in the paper that I maybe didn't mention, Anytime Weighted Astar actually usually, it's the idea of the termination that's hard, right? So right, Anytime Weighted Astar, even if it doesn't get to finish the search and prove that it was the optimal path, well, more often than not, it's actually just getting the optimal path pretty quickly anyway, and then it spends the whole rest of its time proving it. So even with strict time budgets, you might be getting very, very comparable or even equivalently optimal paths using this approach. I think this is really exciting. I want this to be implemented more in games. Please ask any questions in the comments below. Otherwise, this is the first anytime algorithm we're going to be having a look at. In the next video, I'm going to talk through CPD search. CPD search is the next anytime algorithm for these dynamic environments. It's going to take the idea of CPDs that we've already seen and know, and it's going to translate those into problems where there's these shifting costs in these dynamic environments. So please join me here for that video. Otherwise, thank you so much for watching, and see you in the next video.